Hi everyone, in this video I will be putting to the test an idea I've had for the last few years about a possible origin to alchemy, specifically the aspect of alchemy about turning lead into gold. Now, a lot of you might be familiar with this particular experiment known as Golden Rain, which is a classic science experiment done in classrooms and things like that using lead nitrate and potassium iodide. Now, this is an experiment that uses a lead compound and turns it into a substance that very much looks like gold. And if you didn't have a knowledge of atoms and molecules and other modern chemistry, you might actually believe that you were close to creating gold from lead if you were able to accomplish this experiment. Now, I have no historical evidence at all that this actually is an experiment that led into the origins of alchemy, but I'd like to test it because I believe it is a possibility. And if you do actually have some historical knowledge in this area, please do leave it in the comments below. What I would like to test is if this experiment would have even been possible using ingredients that were available at the time when alchemy was first coming about. This would have been 2,000 or 3,000 years ago. Now, the compounds that I need to isolate are a lead compound, either lead nitrate or lead acetate, and potassium iodide. Now, the first thing that I'll do is I will try to isolate potassium iodide from seaweed. Okay, so here is the first step that I will take to isolate an iodine compound from seaweed. And since I don't live near the ocean, I ordered this ground seaweed, which is used as fertilizer and things. I ordered a bag of this online. And I have this kiln here that I usually use for making charcoal. I have a small can that sits inside a bigger can, and you create a fire. This is similar to, if you've seen videos on things called rocket stoves, this is similar to a rocket stove that I use for cooking charcoal usually. But what I'll do is I'll set my smaller can inside the larger one, inside of this stove here, and fill that small can. I don't think I'll fill it all the way, but I'll fill it maybe halfway with this powdered seaweed, which smells terrible, by the way. In preparation for this video, I did do a small test trying to isolate some iodine from a small amount of this ground seaweed, and I didn't get a whole lot of iodine. I got a little tiny bit. So I'm going to try to get more this time by cooking off more of this seaweed here than I did the first time. So the purpose of this process that I'm trying to do here is I'm taking this ground seaweed, which seaweed is a natural collector of iodine. That's why I'm using seaweed and not just any other organic material. I'm going to be taking this ground seaweed and heating it in this furnace to drive off all the organic components that I can. And that should just leave behind iodine, salts, and things like carbonates and chlorides that don't burn away. You might wonder why I'm cooking the seaweed in a separate can rather than just tossing it in with the burning wood underneath. The reason that I'm doing that is because the wood ash is going to contain very little iodine, and so I don't want to contaminate the seaweed ash with that wood ash. I want the iodine that's in the seaweed to remain as uncontaminated as possible. Okay, it looks like the seaweed has lost about half its volume. I think it will probably get down to about 1/4 of its volume when it's finally finished cooking. So I'll continue with this, but you can now see that the gases that are being cooked off the seaweed are just burning as they exit the can here. Now, that's actually a bad thing in this case because I'd like for some of the atmospheric oxygen to be able to get down into the charcoal that's being produced itself, so it can burn away the carbon and turn that to ash as well. I don't know if I'll be able to do that or not. Right now, the gases that are being cooked off are kind of taking all the oxygen and burning it before it could get down that deep into the can. So maybe I'll blow a little bit of oxygen down into these ashes as I cook the last little bit. But we'll see what it looks like in about another 10 minutes or so. Okay, now I have burned the seaweed down to at least charcoal, if you can see that. It's very dark still, so it has quite a lot of carbon left in it. It seems like this, the seaweed is resistant to burning all the way to ash. I've found this is the case with some organic materials, so hopefully there is enough iodide salts in here, either potassium or sodium iodide, that I'll be able to extract it. So the first thing that I'll do is I'll add some distilled water to the burnt, ooh, you can see it's very, very hot still. I'll add some distilled water to the remains of this seaweed. So what this is doing, having added distilled water, is I'm attempting to dissolve any iodine compounds that were extracted from the rest of the organic material in the seaweed. And so those iodine compounds should dissolve in the water, and things like carbon, any of that will be undissolved, and then I can pour it through this filter over here, and hopefully the iodine compounds will flow through the filter. They will still be dissolved in the distilled water, and we will be able to later collect those. So I will go ahead and pour it through this filter and make a big mess at the same time. You can see that this will probably be quite a long process for me to filter all of this liquid, but it is coming out quite clear on just a single pass through a coffee filter. All right, so here is my result. I'm going to let this sit for a while to let all the remaining microscopic pieces of charcoal that are still suspended in the water, I'm going to wait for those to settle to the bottom. Then I will pour this off into this beaker. I probably won't be able to fit all of it in at the same time. Well, maybe I will, because this is 250 milliliters up to the last measuring marks. But then I will throw the liquid on my burner and distill it down to a much greater concentration. All right, so this is ready to go throw on the burner outside and boil off the excess water to see how much potassium and sodium iodide I am left with. And in the meantime, I have another thing I'll need to throw on the burner. I now need to work on the lead compound that will be part of this reaction. Now, the lead compound that would be used in modern times to produce this golden rain reaction that I'm striving for is lead nitrate. But there's a problem in that lead nitrate requires nitric acid in order to make it. Nitric acid, as far as I can tell, was not invented until about 800 years ago, and the origins of alchemy date back thousands of years. So there's a problem there in that lead nitrate couldn't have possibly been used in this reaction unless nitric acid was discovered way before it was documented. So I'm not going to rely on lead nitrate for this reaction. Instead, I'm going to try a process using lead acetate. Now, lead acetate was definitely around thousands of years ago because it was used by the Romans as an artificial sweetener. As you can imagine, this was not a particularly healthy sweetener, and it has been documented that several bodies discovered from that time did die from lead poisoning, probably from lead acetate. So here I have a piece of lead, which would definitely have been available during ancient times. And to form lead acetate from lead is a fairly simple process. I will shave off small strips of this lead into this beaker, and being in small pieces will allow it to react more quickly. So now I need to convert these lead shavings into lead oxide, which could be done by heating the lead until it burned. However, that is not especially good for the environment, so instead I will use hydrogen peroxide to convert this to lead oxide in solution. While this is probably not the method that would have been used to produce lead oxide in ancient times, it is much safer, and I don't think lead oxide will be the deciding factor in whether or not this could be done. And notice how quickly this started reacting. You can already see bubbles forming from hydrogen gas being thrown off of the hydrogen peroxide as it oxidizes the lead shavings, turning them into lead oxide. Now, from this point, we can directly convert the lead oxide as it is forming into lead acetate by adding some vinegar to this solution. Interestingly, there is a fog forming at the bottom of this beaker, which seems to indicate that either a lot of lead oxide is being produced that hasn't yet been converted into lead acetate, or that is the lead acetate and it's less soluble than I expected. So we'll see if we can dissolve that as it continues to form. But what I will do is I will put this on high heat, because eventually, once all the lead has been reacted, I'll need to boil off all of the hydrogen peroxide and excess vinegar so that we're left with nothing but pure lead acetate powder at the bottom. All right, here is my filtered iodine solution, and I'll just set this on the burner. And here is my solution of lead acetate, which is still reacting. There's still solid chunks of lead in this beaker. So we'll go ahead and turn this burner on low and just wait for the lead acetate to fully form and dissolve all that lead into solution. And in the meantime, we're trying to boil off both solutions so that we get down to the pure substance in each by the end. So right now I'm still waiting on the beaker containing the lead solution to fully distill because I've continued to add more vinegar to that beaker as some distills off to try to convert as much of the lead oxide that is formed from the hydrogen peroxide into lead acetate. It seems to be a slower and more difficult process than I anticipated. So hopefully that lead oxide does fully convert into lead acetate, but we'll see how that turns out in a little while. But in the meantime, my beaker with the iodine solution has distilled plenty, and in fact, I did let it boil a little too long, and as it lost moisture content, it made a sludge in the bottom that ended up splattering over the burner. So I did lose quite a bit of the minerals that condensed because of the splattering. So that was a little bit inconvenient. I do have enough left over though that we can now test for iodine in this solution and make sure that I did in fact get enough to continue on with this reaction. So in this vial, I have a 50-50 mixture of hydrogen peroxide and vinegar, and it just so happens to be a happy coincidence that I can use these same two chemicals that I'm currently using to convert the lead into lead acetate to test for iodine as well. So in this little eyedropper, here is some of my concentrated iodine solution. So we can put this in here, and we'll soon find out if in fact I did produce any iodine. And there is the yellow color that I was looking for. That is a sure indication that I have in fact produced some iodide salts in my solution. The downside is this does not look to be very concentrated. It should be a very dark yellow color or even red. By the look of this, the iodine must not have been very concentrated in the sample of seaweed that I have. And so I may not have enough to carry out the Golden Rain experiment with this iodine alone. I would probably need a good quantity more seaweed, or I would need seaweed that is more potent in its iodide content. So I think what I'm going to do now that I know that I can isolate a small quantity of iodine from a small quantity of seaweed that I have here, I will supplement this amount with some potassium iodide that I have purchased. Now I'm doing this under the assumption that someone in ancient times would not be limited by a small quantity of seaweed. They could have burned a whole lot more and produced a lot more iodine. So I don't think this is cheating too badly. So my beaker with my lead compound turned brown at the end of the point where the liquid was being boiled off. And almost certainly this is due to contaminants in the vinegar, sugars and various other organic compounds that once the high heat was able to affect them when the liquid had boiled off. They started to caramelize. All these sugars in the vinegar started to caramelize. So maybe we can filter some of this out, some of this color, and some of it may stay dissolved in solution. So the first thing that I'm going to do is at least purify this and get rid of any of the remaining lead oxide and hopefully just be left with lead acetate. So I'm going to pour a little bit of distilled water into this beaker. And here is our solution. We'll wait for this to dissolve all the compounds inside. And we will filter this to see what we have left. That does not look great. That looks like milky coffee. So apparently filtration in this sense is not a good option. So what I'm going to do is I'll wait for this to finish filtering. We'll see what all is left on the filter paper, and then I'll wait for this to settle. And we should see the lead oxide that's still remaining in solution settle to the bottom, and then maybe I can pour off the remaining liquid. Maybe that'll work a little better than filtration to get the lead acetate out of solution. Well, here is the moment of truth. I have my, my iodide solution right here, and I have my lead acetate solution right here, if in fact I did create lead acetate, which I believe I did, but we're about to find out. Now, when I combine these two chemicals, the potassium and sodium iodide in this container with the lead acetate in this container, we should see a precipitate that is bright gold, a precipitate of lead iodide. So I will take a small sample at first and drip it. Ooh, look at that. Wow. Wow, okay, I gotta get a close-up of that. That is sweet. Okay, let's put a little bit more in. Wow, no way. That almost looks as vivid as fluorescein, which is a highly fluorescent tracing dye. Wow, that looks almost exactly like fluorescein. A little bit more golden color. Wow, that is beautiful. So as far as I know, this is the first time that this reaction has been done on YouTube using lead acetate rather than lead nitrate. Which, using lead acetate, as I mentioned at the very start of the video, was one of the criteria to make this somewhat plausible to have been done in the time when alchemy was first getting started. Now at this moment, this does sort of look like gold in suspension, maybe by color, but it's not until we further process this that you'll really get to see how much this looks like gold once it fully crystallizes. I want to add an excess of iodine so that I'm sure I have created all of the lead iodide that is possible out of my lead acetate solution. So here's what has to happen now. This is clearly lead iodide from the very bright color, which is an awesome result. I was not sure that I was going to be successful in this using lead acetate and iodine mostly extracted from seaweed. But so far this just looks like a really yellow solution. It's only after I have dissolved this compound and we have allowed it to recrystallize that we will really be able to see how much this really looks like gold. So we should only have to heat this solution to maybe 150 degrees or so before we see it go completely clear as the lead iodide dissolves. There might be some slight coloration just from the contaminants that were left from the vinegar in the boiling process earlier, but I might be able to get rid of that if I filter the resulting crystals and put them back in pure distilled water. I changed my mind last minute and did decide to filter the crystals before throwing this solution on the heat, mostly because I wanted to get rid of all the potassium acetate that was a byproduct of the reaction that formed my lead iodide. After being on the heat for quite a long time, despite what I said earlier, my solution didn't turn 100% clear, and I think that's just because I didn't have quite enough water to dissolve all of the lead iodide into solution. I think this is about as good as this will get at this point, so I'll take it off the heat, and now I just need to wait for the crystals to form. This is exactly the result I was hoping that we would see. If you've ever seen gold flakes suspended in a vial before, this looks very similar, until maybe you get the light behind it and realize that it's transparent. If I take some of these crystals out and dry them on a paper towel, now the resemblance becomes really similar. In fact, more so than I think even fool's gold, if you've ever seen that before. I think that this absolutely could have fooled someone into believing they were close to creating gold with this reaction, and even from lead itself, which is of course one of the more famous goals of alchemy. So let me know what you think of this experiment below. Do you think I did a good job with this video in showing that this actually could be done using ancient technology? The only modern technology I used in this video was this hot plate, which of course could be replaced with any sort of burner or candle in ancient times. So I don't think that is a limiting factor. Let me know if you have any other ideas about experiments that could have led into the ideas of alchemy. I hope you enjoyed this video, and if you did, please consider supporting my channel on Patreon. I could really use your support, especially if I'm going to continue producing quality over quantity. On YouTube, that's very hard these days, so Patreon support would be awesome. Thank you for watching, and I'll see you next time.